In the course, you read and heard a good deal about the processes of seafloor spreading and plate tectonics. Seafloor spreading means that continents now separated by wide oceans were originally part of a single continental mass. One of the major remaining geological problems is how and why continental plates split to form new ocean basins. Here's Ian Gass.
The fit here of South America to Africa is excellent, and there can be little doubt that less than 200 million years ago there was an Afro-American supercontinent. Why did it split up here? Why didn't it split up the Benue Trough and across Algeria, where there are known major fault systems? And the simple answer is, we don't know. The geological evidence that might be preserved in the oldest parts of the oceans has been covered by sediments, and what evidence there was on land has been subjected to 200 million years of weathering and erosion. So if we can't explain why the South Atlantic, one of our most recent ocean basins, why it formed, what hope is there of deducing how and why continents split? Now, fortunately, we have a still younger ocean here, the Red Sea. And here we have a transcontinental split between Africa and Arabia that's occurred in the very recent geological past. And we know there's an active constructive margin down the axis of the Red Sea. So if we're going to answer the questions of how and why the continents split, then this is the place to investigate the problem. Of course, what you notice straight away is the parallelism of the coastlines. Note here in the north that the coastlines are straight, continuing the line of the Gulf of Suez. And then they start to zigzag, but together, until at the southern extremity, Africa and Arabia are only about 50 kilometers apart. When you fit Arabia back to Africa, Arabia has to be moved southwestwards, and over most of its length, the coastline fit is excellent. Obviously, there's been a lot of transcurrent movement here in the Gulf of Aqaba, and we have problems of overlap here in the north, and even more so down here in the south. But the fit is so good that you intuitively feel that there must be something in the proposal that in geological time there was until recently one continent. And if there was one continent, is there or was there something about that continent that made it especially prone to splitting? And the answer seemingly is no. Geophysically, it is a typical piece of continental plate with some 35 kilometers of cealic crust consisting of granitic and metamorphic rocks overlying peridotite upper mantle. The crust, which we often call the basement, is not particularly old. It was formed sometime between 1200 and 500 million years ago. During the Phanerozoic, the last 540 million years, nothing much has happened. The continental plate had formed and was moving over the Earth in response to several phases of seafloor spreading, and on the way it collected a sedimentary veneer that in turn has been largely removed by erosion. There were no major tectonic or magmatic episodes. Then, quite suddenly, about 30 million years ago, basalt started to pour out over the southern area on top of an eroded surface. And some 10 million years later, all this area had been covered by lavas in places to a depth of 3 kilometers. But there was something else going on at this time. Look at this outcrop of basement. And these escarpments. This erosion surface was formed at near sea level, but it's since been raised by nearly 2 kilometers above sea level. The whole region has been updomed, mostly around here. And one possibility to explain the initial formation of the Red Sea is that this bulging of the crust caused stretching across the line of the Red Sea and the development of a trough or graben. Or perhaps the two plates moved apart before the uplift happened. Or perhaps there are elements of both processes. But one way of tackling this problem is to look at the sediments. For the history of any stretch of water, the Red Sea included, is recorded in the sediments that are deposited there.
For nearly 500 million years before the Red Sea opened, this region was geologically stable. terrestrial sediments were deposited over almost the whole area. These sediments were the deposits of a large river system that drained an upland region in the south and flowed northwestwards into an ocean. The coastline of this ocean was a fluctuating one. At intervals, the ocean advanced southward and eastward, depositing marine sediments that are interbedded with the sandstones. There are shales with plant remains, and the marine sediments include limestones rich in the remains of oysters. There are also chalks and shelly limestones, suggesting a shallow water, high energy environment, rather like that of the Florida Keys today. Between about 30 and 40 million years ago, the sea retreated northwards, and there was a major change in the pattern of sedimentation. Coarse conglomerates were deposited in so-called Piedmont fans, which typically form where rivers draining highland areas flow abruptly out onto low ground. They were formed as a result of uplift of the margins of the embryo Red Sea, and they accumulated along the line of the present Red Sea. The flanks continued to rise, and the geological evidence suggests that about 20 to 25 million years ago, a marine trough formed between them. It was open in the north, but was closed to the ocean in the south. For a substantial part of the succeeding 15 to 20 million years, sea level fluctuated greatly in the Red Sea trough, as it was repeatedly cut off from the ocean to the north. About 5 million years ago, the Red Sea became open to the south. Sea level returned to normal, and the deposition of evaporites ceased.
Well, if Africa and Arabia were one until, say, 20 million years ago, as the sediments indicate, and if the coastline fit is still the best bet, we still have two problems, both involving coastline overlap. The biggest overlap is here in the southern area, and it's the Afar Triangle. But this area is known to consist largely of recent basalts erupted within the last 20 million years, so they can be ignored in any 20 million year reconstruction. There is a minor complication, however, and it's this ridge of high ground, the Danakil Alps. These mountains are underlain by basement rocks. How and why they are there, surrounded by basaltic lava flows, is a problem. The tectonic situation in the area where these three plates join is complex. There hasn't been much movement between the Nubian and the Somali plates, but when Arabia started to move away from Africa, a fragment of the African basement seems to have got torn off in the spreading process, and as it wasn't attached to Arabia, it was left behind, stranded as a fragment of crust, a microplate. But note that as the Arabian plate moves relative to the African plate, both the Red Sea and the Gulf of Aden are formed together. So it would seem that at the southern end of the Red Sea, if we dispose of the Afar Triangle, the coastal fit is good. But the northern end of the Red Sea still presents problems. Movement must have occurred here along the Aqaba Transform, and this area, the Midian Peninsula, upsets the good coastal fit. This is obviously another complication, and to understand this area we need someone who knows the region well. Doug?
Well, here we are. We've moved some 1,200 kilometers north up to the head of the Red Sea, where it bifurcates into the Gulf of Suez and the Gulf of Aqaba. Now, these two are quite different from one another. The Gulf of Suez continues the trend of the Red Sea, but unlike the Red Sea, it is very shallow. It is nowhere deeper than 200 meters. Geologically, it is a graben structure, and on the satellite image, we can see the boundary escarpments on either side quite clearly, here on Sinai and here on the African side. Also, we can see the horse blocks within the graben, one there, another there, and another there. There must, of course, have been some extension across the region to allow the graben blocks to fall, but that extension can only amount to quite a small part of the present width. Now, this information is quite important, because it does mean that in any reconstructions that we make of the evolution of the opening of the Red Sea, in none of those reconstructions can we close the Gulf of Suez. The Gulf of Aqaba is relatively narrow, it's steep-sided, and quite deep. Locally, it achieves depths of 16 to 1,700 meters. Now, this line is the line of a major fault, and the Gemini astronauts were able to look along this fault, and fortunately, they photographed it for us. Here we see the trend of the Gulf of Aqaba, and then you can trace the fault all the way up Wadi Araba to the Dead Sea, and it continues beyond. The line of the fault is quite clear there. Now, the displacement on the fault is sinistral, that the rocks facing you have moved to the left, and we can demonstrate that here. Just here in the northeast corner of Sinai, there are outcrops of quartz porphyry. Similar quartz porphyries occur in Jordan, on the other side of the fault, up here near Petra. The distance between the two along the line of the fault is 105 kilometers. Now, elsewhere along the fault, we can demonstrate that the movement took place in two main phases. One, relatively recent, within the past 5 million years, of 40 to 45 kilometers, and the other, somewhat earlier, of 60 kilometers, the two together amounting to 105. Now, if the Red Sea opened by drift of Arabia away from Africa, then the separation can only have been achieved by movement along this line. It was the almost perfect match in the configuration of the opposing coastlines which first drew attention to the possibility that the present Red Sea was the result of the drift of Arabia away from Africa. However, bear in mind that we cannot close the Gulf of Suez. It is a graben underlain by continental crust. Here in the north, the fit is almost perfect, except for the small peninsula of Midian, which overlaps Africa. Although the peninsula mostly comprises late tertiary sediments, there are inliers of basement rocks, so it's partly at least continental crust, and it projects into the Shield of Africa where there is no re-entrant to accommodate it. These rocks lie immediately adjacent to the Aqaba Fault, and it's likely that they were originally parts of the Arabian Shield, which became displaced during movement along the fault. So we can discount them in this fit. We know that a sinistral movement of 105 kilometers has occurred along the Aqaba-Jordan Valley Fault. The trouble is, such movement does not open the Red Sea to its present position. Something is obviously wrong. Perhaps our assumption of a tight coast-to-coast fit was in error. So let us start from a position about which we are certain, namely present-day geography. Move the Arabian Plate 105 kilometers back along the Aqaba Fault. This brings the northern coastline of Saudi Arabia into almost direct continuity with the boundary escarpment of the Suez Graben in Sinai, and it makes the northern sector of the Red Sea continuous with the present Gulf of Suez Graben. The implications could be that prior to the initiation of spreading, the northern part of the Red Sea was part and parcel of the Suez Graben. Well, here once again, the astronauts have given us a God's eye view looking down the Gulf of Suez into the northern part of the Red Sea. Had they been in space, say 20 million years ago, somewhere at the beginning of the Miocene, this is what they may have seen.
So neither of the problem areas have turned out to be much of a problem. And although Doug Sherman believes that the northern part, at least, started as a graben and needs some continental crust offshore, we still have a near-perfect coast-to-coast fit. We're also sure from the sedimentary evidence that the whole evolution of the Red Sea has occurred in the last 30 million years. Up until then, there was a low-lying landmass to the south around here, and rivers were draining northwards into broad, warm, shallow seas. Then, about 30 million years ago, basalts erupted all over this southern area. And they were erupted over a flat surface. And the area began to sag under their weight. Remember, there were about 3 kilometers of basalts in some areas. By 20 million years, all this activity had stopped, and a trough had begun to form along the line of the present-day Red Sea. The flanks had begun to rise, and rivers were draining into this linear depression. But at no time was the Red Sea region above sea level, because we find marine sediments deposited in the trough throughout the period. The ancient continent was beginning to split, with the Arabian plate moving northwestwards away from Africa. But how and why did it all happen? To answer that question, we need to look at the Earth beneath the Red Sea itself. There is a variety of good evidence to suggest that all the marine area in the southern Red Sea is underlain by oceanic crust. Glomar Challenger has drilled across here in the deep-sea drilling project, and their cores have penetrated thick evaporites. Certainly, the axial trough is underlain by oceanic crusts, for oceanic basalts have been dredged from the floor. And these basalts, together with those from volcanic islands, are comparable in all ways to the basalts of major oceans. Furthermore, linear magnetic anomalies have been detected over the axial trough, and these, together with other geophysical evidence, such as heat flow and earthquake foci, leave no doubt at all that an active constructive margin underlies the axis of the Red Sea median trough. And relating the linear magnetic anomalies to the magnetic polarity reversal timescale suggests that the spreading rate was just under 1 centimeter per flank per year. Now, as the Red Sea around here is about 400 kilometers across, it should, at this rate, take about 20 million years for the Red Sea to form by seafloor spreading. So even more convincing in this respect is that just here, in southwest Saudi Arabia, right on the coastline, there's an outcrop of oceanic basalt that dates at 21.5 million years. So it all fits very nicely. All the Red Sea is underlain by oceanic crust, formed at a median constructive margin, with a constant spreading rate of about 1 centimeter per flank per year for the last 20 million years. Now, could it all be that simple?
Here's a magnetic profile across the Red Sea. The peaks in the profile are positive anomalies. The troughs are negative anomalies. Over the central or axial portion of the Red Sea, the anomalies are very large. Further out, however, the anomalies of rather smaller amplitude, and they look smoother. Magnetic anomalies aren't significantly affected by overlying evaporite deposits, even when, as here, they're as much as 5 kilometers thick. So the different appearance of these flanking anomalies is not due to evaporites. The anomalies show symmetry about the axis of the Red Sea, so the magnetic anomaly pattern is consistent with seafloor spreading in the Red Sea. Although there's still some doubt about how many phases of spreading there were, and exactly when spreading began, it's clear that there was no trace of continental splitting and new ocean formation much before about 30 million years ago in this area. When splitting began, it happened rapidly in geological terms, over a time span of only a few million years.
What we should be asking now is how and why did it all happen? There's no doubt that Africa and Arabia were one prior to 30 million years ago. And before that time, as far as we can tell, there was no indication that anything was about to happen. At that time, 30 million years ago, the nearest constructive margins were down here in the Atlantic and over here in the Indian Ocean, and there was a major destructive margin between Africa and Arabia and Eurasia, and fold mountains were being formed along the southern margin of Asia and Europe. So why did the split occur here, when and where it did? Well, first, the part of the continent that split is relatively young, and intuitively it would seem to be a far better candidate for splitting than the older cratons, which are underlain by 400 kilometers of old, cold, dense upper mantle. Second, the earliest signs of activity were the eruption of vast quantities of basalts in the Yemen and the Ethiopian trap series, and here this means that magma must have been produced in the underlying upper mantle. Third and last, it seems significant that at about this time, say 40 million years ago, the combined Africa-Arabia plate, which had been moving northeastwards, slowed down and began to stop, possibly because it impinged upon the other major continent, Eurasia to the north. Now, there's very good evidence that heat flow from the mantle is uneven, and when the African plate stopped, it's possible that zones of anomalous mantle formed above the areas of high heat flow and beneath the crust, the grey area in this cross-section. The production of low-density mantle requires an increase in volume, and this can best be accomplished by vertical uplift on a regional scale. Within the anomalous mantle, discrete pockets of magma developed, from which the trap series basalts were erupted starting 30 million years ago. Eruptions continued intermittently for the next 10 million years, by which time most of what is now Ethiopia and Yemen were covered by basalts up to 3 kilometers thick. When this volcanic phase stopped, the weight of these lavas caused the crust to sag into a shallow basin. When volcanic activity restarted about 20 million years ago, it was concentrated along the line of the Proto-Red Sea, and the Arabian plate began to move away from Africa as basalts formed along the Red Sea axis. This was the beginning of the ocean floor, and as it developed, the Proto-Red Sea began to take on a linear form. The flanks rose, the seawater occupied the trough, and at times the basin was isolated and evaporites were deposited. Fine, the lines of weakness are there, and the area is underlain by magma-lubricated mantle. But why should these develop into the Red Sea and Gulf of Aden new constructive plate margins? It's speculation, but I think that by 20 million years ago, the plate tectonic system got stuck here in Europe, where Africa and Europe had collided. The Tethyan sediments were compressed into the Alps. Further to the east, the Arabian plate still had some distance to go. Ocean still existed between the two plates, and subduction continued. Now, with subduction, the cold, down-going oceanic plate is denser than its surroundings, and so it descends under its own weight. This is called the sinker effect, and some earth scientists believe that the pull it exerts on the rest of the plate is a main factor in seafloor spreading. Now, if this bit of oceanic crust was attached to the Arabian plate, then could this have pulled the Red Sea open? With lines of weakness along the Proto-Red Sea and the Gulf of Aden, all that has to happen is for the northern section to split and lateral movement to take place along tectonic tramlines. And these tramlines can be recognized today as the Jordan-Aqaba Fault to the north of the Red Sea and the Owen Fracture Zone to the southeast in the Indian Ocean. In this model, the Red Sea, up to the line of the Aqaba Fault, is floored mainly by new ocean crust. The process continues as the Red Sea widens, and the end will only come when Arabia moves towards Asia and then finally stops.